Hello everyone. So last time we looked at Laplace transform of antiderivatives. And we looked at Laplace transform of integral of 0 to t f of tau d tau. So this function called area function is an antiderivative for f, for small f, because according to FTC part 1, if you differentiate this function here, it will be f of t. So as long as small f is a continuous function, this function is differentiable, and derivative of this function is f of t. Therefore, this function is antiderivative of f. Now, Laplace transform of this function, we saw that can be written as 1 over s times Laplace transform f of t itself. And we use this formula to solve integral equations. So the equation is where integral of some function is involved, and the goal is to find that unknown function. We saw one example last time. Now let's look at another example. Example, solve the following integral equation. So the equation is t squared equals integral 0 to t e to power tau x of tau d tau. The goal here is to find x of tau. So this x of tau is the unknown function, and we want to find it. Now, in order to find x of tau, let's apply Laplace transform. Laplace transform to both sides of this equation. Then what do we get? We get Laplace transform t squared equals Laplace transform integral 0 to t e to power tau x of tau d tau. Now, Laplace transform t squared, we have a formula for it in the table. Laplace transform t to power n, we know it's n factorial over s to power n plus 1. So this will be 2 factorial over s to power 3, or 2 over s cubed, equals, now Laplace transform of integral, we just saw that Laplace transform of integral of a function is 1 over s times Laplace transform of the function itself. So it's going to be 1 over s times Laplace transform e to power t x of t. Now, Laplace transform e to power t x of t, we had a formula for it in our table from before. If you remember, Laplace transform e to power at f of t, well, can be written as capital F of s minus a. If capital F of s is the Laplace transform of f. Capital F of s being Laplace transform f. So this is a formula we have seen before for Laplace transform e to power at times a function. So here we have Laplace transform e to power t x of t. So it's going to be f of s minus 1, 2 over s cubed equals 1 over s times f of capital F of s minus 1. Because for e to power at f of t, we have capital F of s minus a. So for e to power t x of t, we have capital F of s minus 1. And capital F of s is Laplace transform x of t. Here, capital F of s equals Laplace transform x of t. So what do we get now? We can cancel 1 over s from both sides. We get 2 over s squared equals capital F of s minus 1. And if I change s to s plus 1, I'll get capital F of s as 2 over s plus 1 the whole squared. So capital F of s is 2 over s plus 1 the whole squared. Now I want to find x of t. X of t will be in inverse Laplace transform of capital F of s, which is going to be inverse Laplace transform of 2 over s plus 1 the whole square. Now, if I had 2 over s squared here, well, I know that inverse Laplace transform of 1 over s squared is t from the table. Table tells me that t is inverse Laplace transform of 1 over s squared. So if I had 2 over s squared, I would have considered 2t. But this is 2 over s plus 1 the whole squared. But basically, we have a shift in s. But we just saw how we can obtain a shift in s. If I multiply my function with e to power at, I will have a shift from s to s minus a. Here I have a shift from s to s plus 1. So I need to multiply with e to power minus t. So we just said that if I had 2t would be inverse Laplace transform 2 over s squared. Now if I compare this function with this function, there's just a shift. And in order to create that shift, I just need to multiply this function here, 2t, with e to power minus t. Because according to this formula, when I multiply my function with e to power at, I will have a shift from s to s minus a. So in order to create a shift from s to s plus 1, I need to multiply with e to power minus t. So that means 2t e to power minus t will be inverse Laplace transform of 2 over s plus 1 the whole squared. And therefore x of t here is 2t e to power minus t. So this is the final answer for this integral equation. So my unknown function x of t that satisfies this integral equation is 2t e to power minus t. All right, now the next topic we want to look at is called convolution. So far we looked at Laplace transform of, let's say, derivative of a function. So this can be written as like s f of s minus f of 0. Laplace transform of antiderivative, Laplace transform of certain functions. So this one besides 1 over s f of s, and so on. Now, what about Laplace transform of product of two functions? We haven't looked at it yet. Laplace transform of product of two functions. So suppose that f of t and g of t are two functions whose Laplace transforms exist. Now, what can I say about Laplace transform of product of f and g? So can we say Laplace transform f of t times g of t is same as capital F of s times capital G of s, with capital F of s being Laplace transform f and capital G of s equals Laplace transform g. So can we say that Laplace transform of product of two functions is product of Laplace transforms? So the answer is no, as long as we consider the standard product here. No. You can check it as an exercise. Consider two functions f and g. Multiply them, take Laplace transform, and if you compare it with product of the Laplace transforms, you will see that these two are not equal in general. However, if we consider a certain type of product between two functions called convolution, then the property above will hold. So as long as you consider the standard product of two functions, this property unfortunately does not hold. But if instead of standard product, I consider a certain type of product called convolution, so instead of f times g, if I consider f convolution g, then the Laplace transform of f convolution g can be written as f of s times g of s, as desired here. So let's define the convolution, this certain type of product, which is called convolution. So let f of t and g of t be piecewise continuous functions as before. Piecewise continuous functions. The convolution of f of f and g denoted by f star g is defined as follows. So f star g at t is equal to, is defined as integral 0 to t f of tau g of t minus tau d tau. So left hand side is a function of t, right hand side is also a function of t, and the integration is over tau. So note that a simple substitution shows that the formula can be also written this way. It can be also written as integral 0 to t g of t f of t minus tau d tau, which is same as g star f of t. So similar to the standard product where f times g is same as g times f, here also for this certain type of product called convolution, f convolution g is same as g convolution f. Why? Because this integral can be easily shown that it's same as this integral. You just need to use a simple substitution. So I can leave this as an exercise. A simple math 114 exercise, a simple substitution that shows this is same as this. Now, other properties of convolution. So one property is that similar to standard product, we have a commutative property, meaning that f star g is same as g star f. Now, what about the other properties? Other properties of convolution. So this one I can, if I call it property 1, and then the second property, let's say CF convolution G is same as C times F convolution G, where C is a constant, C in R is a constant. So this one also we can easily use the definition of convolution to prove this property. And then the next property, associative property, meaning that F star G star H is same as F star G star H. So again, similar to the standard product where we have F times G times H is same as F times G times H. Again, here we can say F convolution G convolution H is same as F convolution G, then convolution H. Now this is convolution of two functions. How we define convolution of two functions. Now with this definition for convolution, we can now talk about this Laplace transform property, that instead of f times g, if we replace it with f convolution g here, then we can say the Laplace transform of f convolution g is equal to capital F of s times capital G of s. So for Laplace transforms, so the important property or important theorem is as follows. Highlighted with red theorem. Let f of t and g of t be piecewise continuous functions piecewise continuous functions which are of exponential order. Remember, piecewise continuity and being of exponential order were the conditions that guaranteed for us the existence of Laplace transform. So under this condition, we have a guarantee that Laplace transform of f and Laplace transform of g exist. And suppose that and let capital F of s be Laplace transform f and capital G of S be Laplace transform G. Then we can say that Laplace transform F star G of T is equal to capital F of S times capital G of S. Where F star G of T is integral 0 to T F of tau G of T minus tau d tau as defined above. So Laplace transform of convolution of two functions is the product of their Laplace transforms. All right, now for proof of this theorem, let's skip the proof. But instead, let's look at an example. Let f of t equals e to power t and g of t equals t. Let's look at convolution of these functions and then take or apply Laplace transform to the convolution, and let's see what happens. So what will be the convolution of f and g here? So let's compute the convolution f star g of t. Now, how do we define f star g of t? F star g of t, we said it's integral 0 to t f of tau g of t minus tau d tau. Then this will be integral 0 to t e to power tau times t minus tau d tau. Now the integration is over tau. So t can be taken out of the integral. This t here can be taken out of the integral because integration is over tau. So then I'll have t times integral 0 to t e to power tau d tau minus integral 0 to t e to power tau times tau d tau. Now I need to calculate these two integrals. So for this one, we need antiderivative of e to power tau, which is e to power tau itself. And I need to calculate it between 0 and t. So that will be e to power t minus 1. And for this one, what is the antiderivative of tau e to power tau? Well, we can use integration by parts in order to compute this antiderivative. It can be shown that it will be tau e to power tau minus tau. So this is antiderivative of tau e to power tau, which you can check by integration by parts. Like in integral x e to power x can be computed using integration by parts. And then I have to calculate this function between 0 and t. 0 and t, so then I will get t. So this will be t e to power t minus t. If I compute it between 0 and t, I'll get t e to power t minus t. Sorry, this was a tau e to power tau minus e to power tau, not a tau e to power tau minus e to power tau. And then I calculate it between 0 and t. I'll get t e to power t minus e to power t this will be t e to power t minus e to power t. So this is the evaluation of this function at t. Then minus, I need to evaluate it at 0. If I evaluate it at 0, I'll get minus, so 0 e to power 0, that will be 0. So minus 1. And then that will be 1 plus t e to power t minus e to power t. So this is the evaluation at t and minus evaluation at 0. So now I need to multiply t with this function and then minus this function that I have here. So let's see what we get. So therefore, we can say that f star g of t is equal to a t times e to power t minus 1. So that's the first term, minus this term here. So minus 1 plus t e to power t minus e to power t. Then I'll get a t e to power t minus t minus 1 minus t e to power t plus e to power t. So this cancels with this, and then I'll be left with e to power t minus 1. So if my functions are e to power t and t, then the convolution of f and g will be e to power t minus 1. Now let's check, or let's verify that Laplace transform f star g of t is equal to capital F of s times capital G of s. So what are capital F of s and capital G of s here? So here, capital F of s is equal to Laplace transform f of t, which means Laplace transform f of t was e to power t, and we know that this is 1 over s minus 1. Laplace transform e to power at, if you remember, was 1 over s minus a. Laplace transform e to power at was 1 over s minus a. Now, what about capital G of s? Capital G of s is Laplace transform t, g of t, which means Laplace transform t, and that's 1 over s squared. So capital F of s times capital G of s would be 1 over s squared times 1 over s minus 1. And it will be 1 over s squared times s minus 1. So this is capital F of s times capital G of s. Now let's also calculate Laplace transform f star g of t, and let's see whether we get the same answer. Now f star g of t, we just calculated, it happens to be e to power t minus 1. We have to calculate Laplace transform of this function. Now for Laplace transform f star g of t, we have Laplace transform e to power t minus 1, which can be written as Laplace transform e to power t minus Laplace transform t minus Laplace transform 1. Now Laplace transform e to power t, we just said, is 1 over s minus 1, because Laplace transform e to power at is 1 over s minus a. Laplace transform t, we know it's 1 over s squared from the table, and Laplace transform 1, we know it's 1 over s, again from the table. Now let's simplify this. Let's take common denominator. What is the common denominator? Common denominator is s squared times s minus 1. Then here I'll have s squared minus s minus 1 minus s times s minus 1. Now, if I simplify this, it will be s squared minus s plus 1 minus s squared plus s divided by s squared times s minus 1. So now this cancels with this cancels with this, and I'll be left with 1 over s squared times s minus 1. 1 over s squared times s minus 1 is Laplace transform f star g of t, which is exactly same as capital F of s times capital G of s. And that's what I was expecting already, because I was expecting that according to a theorem, Laplace transform f star g of t must be same as capital F of s times capital G of s. So we verified that Laplace transform f star g of t is same as capital F of s times capital G of s. All right, now let's look at an example. Find inverse Laplace transform of s over s squared plus 1 the whole squared. But if I had s over inverse Laplace transform s over s squared plus 1, according to the table, I would have said cos t, because Laplace transform cos t is s over s squared plus 1. But here I have s over s squared plus 1 the whole squared. So let's look at the functions we have in the table. So from the table, we know that Laplace transform sine t is 1 over s squared plus 1. Let's call this one capital F of s. And I also know that Laplace transform cos t is equal to s over s squared plus 1. Let's call this one capital G of s. So we want to compute inverse Laplace transform of capital F of s times capital G of s. If I call this one capital F of s, this one capital G of s, then capital F of s times capital G of s will be exactly this function. S over s squared plus 1 the whole squared. So I want to find inverse Laplace transform capital F of s times capital G of s. But what is it according to the theorem that we just said? The theorem that we just said told us that Laplace transform of convolution of two functions is capital F of s times capital G of s. So that means if you want to find inverse Laplace transform of the function on the right-hand side, it will be simply f star g of t. Laplace transform f star g of t is capital F of s times capital G of s. So inverse Laplace transform of capital F of s times capital G of s will be f star g of t. So I can say that this will be f of s times capital G of s is equal to f star g of t. Because in Laplace transform f star g of t is equal to capital F of s times capital G of s. So we just need to calculate. So here, what is f of t? What is g of t? Here, f of t is sine t and g of t is cos t. Here, f of t plus sine t, g of t plus cos t. So we need to calculate f star g of t, which can be written as integral 0 to t sine tau cos t minus tau d tau. F of tau g of t minus tau d tau. So this is the definition of convolution of two functions. Now, how can I calculate this integral? I can write it as integral 0 to t sine tau, and then I will have cos t. I can expand this, or I can use the addition formulas, because we know that, let's say if you have sine A cos B. So this can be written as 1/2 sine A plus B plus sine A minus B. Sine A plus B is sine A cos B plus cos A sine B. And this one is sine A cos B minus cos A sine B. So if I add them and then divide by 2, the result will be sine A cos B. So what will be this? This will be integral 0 to t 1/2 sine tau plus t minus tau plus sine tau minus t minus tau. And then d tau. So this will be integral 0 to t 1/2 sine t plus sine 2 tau minus t d tau. Now sine t can be taken out of the integral. This can be taken out of the integral because remember the integration is over tau. So t is considered as a constant, sine t also can considered as a constant. I can take it out of the integral, and also 1/2, same thing for 1/2. So 1/2 sine t can be taken out, then integral 0 to t d tau. For the first term, once I take these terms out, then only one will be left. So 1 times d tau, or just simply d tau. And then for the second term, plus 1/2 integral 0 to t sine 2 tau minus t d tau. So then this will be 1/2 sine t, and then integration d tau is tau, which I need to compute it between 0 and t, and that will be t. So this will be tau between 0 and t plus 1/2. What will be the antiderivative of sine 2 tau minus t? Antiderivative respect to tau. Integration is over tau. So I need to multiply this with cos 2 tau minus t divided by minus 2, because if I differentiate this function, I'll get minus 2 sine 2 tau minus t, and minus 2 will cancel out with minus 2. And I need to compute this between 0 and t. So then this will be 1/2 t sine t. And then I need to compute this one. Minus 1/4, I can take it out, minus 1/4. And then inside, I need to put t. If I put t instead of tau, I put t. Cos 2t minus t means cos t. And then if I put 0, so I'll get minus cos minus t, minus cos minus t. If you replace tau with 0 here, you will get cos minus t. But what is cos t minus cos minus t? cos t minus cos minus t is 0. Why is it 0? Because cos minus t is same as cos t. So this is a basic property of cos function. Cos function is an even function, meaning that cos minus t is same as cos t. So you learned this in pre-calculus. So cos t minus will be 0. So this term is 0, and I'll be left with 1/2 t sine t. So we showed that inverse Laplace transform capital F of s times capital G of s, which according to the theorem is same as F star G of t, is same as 1/2 t sine t. Let's look at the next example. Consider the following initial value problem, or IVP. X double prime plus x equals f of t for some function f of t with x of 0 equals x prime of 0 equals 0. So this is the initial value problem here. Find the formula for x of t and find x of t. And find the formula for x of t, let me say in terms of f, of t, and find x of t if f of t is equal to cos t. So first we want to consider the problem for an arbitrary f. Of course, if we don't have f, if we don't know what f is, we cannot find x exactly. But we can find, in the best case scenario, we can hope for finding x in terms of f. So this is what we want to do in the first part, and the second part, we want to know what will be exactly x of t if f of t is cos t. So this is a non-homogeneous equation we have seen before, like methods to solve non-homogeneous equations. This time we want to solve it using Laplace transform. So let's apply Laplace transform to both sides of our equation. Then what do we get? We get Laplace transform x double prime plus Laplace transform x equals Laplace transform f of t, which I can call it, let's say, capital F of s. So here, capital F of s is defined as Laplace transform f of t. Now I also need another notation for Laplace transform x of t. So here I have Laplace transform f of t, which I called it capital F of s. I also need another notation for Laplace transform x of t. So let me call that capital X of s. Capital X of s. Let's define it as Laplace transform x of t. Then Laplace transform x double prime will be s squared capital X of s minus s x of 0 minus x prime of 0, which will be same as s squared capital X of s. Because these terms, according to my assumption, are 0, x of 0 and x prime of 0 are assumed to be 0. So these two terms will vanish, and I'll be left with this term, which is s squared capital X of s. So capital X of s here denotes Laplace transform x of t. So this term will be capital X of s. This term will be s squared capital X of s. So if I substitute back, then I'll get s squared capital X of s plus capital X of s equals capital F of s. The right-hand side was capital F of s. Now if I simplify, capital X of s times s squared plus 1 will be capital F of s. And this means capital X of s will be capital F of s over s squared plus 1. It can be also written as capital F of s times 1 over s squared plus 1. So what will be x of t? Well, we know that x of t is inverse Laplace transform capital X of s, which is inverse Laplace transform capital F of s times 1 over s squared plus 1. And now I have inverse Laplace transform of product of two functions in terms of s, like capital F of s times capital G of s. I know that according to the theorem, this can be written as f star g of t. So this is f star g of t. So this is by theorem above. Since Laplace transform f star g of t is equal to capital F of s times capital G of s. So I can write this one as f star g of t. And what is small f and small g here? Where, well, small f is the function that was given above. Remember, we had a small function f of t in the right-hand side. And what about small g? Small g is the function whose Laplace transform is this capital G, which is 1 over s squared plus 1. So here, Laplace transform f of t is equal to capital F of s, and Laplace transform g of t is equal to capital G of s, which is 1 over s squared plus 1. And Laplace transform of which function is 1 over s squared plus 1? Sine t, according to the table. Therefore, g of t is sine t. So small f of t is the function given the question. Small g of t is the function whose Laplace transform is 1 over s squared plus 1. But the table tells me that sine t is the function whose Laplace transform is 1 over s squared plus 1. So x of t, we wrote it as f star g of t. So for the second part, it was saying that find x of t if f of t is cos t. Well, we know that x of t is f star g of t and g of t is sine t. Well, if f of t is cos t, that means I just need to find the convolution of sine t and cos t, but we just did this in the previous example. So for the second part, g of f of t is cos t. So x of t will be f star g of t with f of t equals cos t, g of t equals sine t. So that means x of t will be 1/2 t sine t. See previous example. In the previous example, we showed that the convolution of sine t and cos t is 1/2 t sine t. So x of t here, which is f star g of t, will be convolution of sine t and cos t, which will be 1/2 t sine t. Okay, guys, so that's all about Laplace transforms. So we looked at the definition of Laplace transform, the conditions for existence of Laplace transform. We found Laplace transform of certain functions, and we created a table, and we saw why Laplace transform is important. And in particular, we saw that once you apply Laplace transform, all the derivatives will be disappeared, and therefore you will have an algebraic equation. You can find your function capital F of S. Once you find capital F of S, you can apply inverse Laplace transform to get the original function back. So that's the most important property of Laplace transform, that you transform a differential equation to an algebraic equation. And we also looked at Laplace transform of antiderivatives. We saw how to use it to find or to solve integral equations. And also today we looked at Laplace transform of convolution of two functions. So we saw once you apply Laplace transform to convolution of two functions, you simply get capital F of S times capital G of S. So we use this to find inverse Laplace transform of product of two functions. So if you have product of two functions in terms of S, like capital F of S times capital G of S, if you want to apply inverse Laplace transform, the answer will be simply F star G of T, or convolution of F and G. Okay, guys. So let's start the new section here, which will be about solving ODEs using series, the new chapter.